Okay, am I audible?
Good afternoon, sir. Yes, sir.
Good afternoon. Yeah, thank you. Okay, shall we wait or let me see. 115, 116. We'll wait for 2 more minutes. Okay. Okay, so this time we'll be seeing what is wideband fading channel. So till last class we saw what is narrowband fading channel, and this time we'll be seeing properties classification of wideband fading channels. Okay, so we have discussed this slide earlier, that is the comparison of narrowband and wideband fading channel. So considering the multipath, let us say that you have the transmitter. Okay, you have the transmitter here, and the receiver here. And if you have multipaths that have the components like the green color, blue color, etc. So if you have three components or four, etc., and if they are closed or packed together, or if they are non-resolvable, then we called that kind of system as a narrowband system, narrowband channel. But if the blocks are kept apart, if they are resolvable, then we'll be calling that kind of channel as wideband channel. So there were some limitations, some disadvantages in narrowband channel. Similarly, there will be some issues that are issues or advantages in wideband channels also. So we'll be analyzing what is happening in a wideband channel today. So keep in mind that the blocks, the multipath components are kept apart, and delta tau, that is the spacing between each component, is greater than 1 by BU, that is the signal bandwidth. So the delay is greater than 1 by signal bandwidth in the wideband, which was not the case in narrowband. So this is the main assumption that we are uh, uh, going to, I mean, which is this is the main consideration that we are assuming when it comes to the wideband channel. Okay, now we'll see some terms. The first term is delay spread. Okay, so we have seen these in the previous slides also, but we'll be revisiting it again. Okay, so we had narrowband channels where multiple blocks are kept together, and similarly we had multiple blocks that are kept apart. The same diagram is shown here. That is this diagram where multiple components, where multiple blocks are kept together is called as narrowband. But if the blocks are kept apart, if the first multipath, okay, first multipath and second, third, etc. are kept apart, then we called that kind of system as wideband channel. So the components are spaced at times like this t minus t0. The first component is spaced at the time t minus tau 0. Second component at t minus tau 1, t minus tau 2, t minus tau 3, etc. Okay, so yeah, that's all about delay spread. So we have seen that if the blocks are kept together, it is called as narrowband, and if the blocks are kept apart, then it is called as wideband. Right? Now we can go to another term. I mean another important technical term that is called as the scattering function. So we all know how we will represent the channel. So in order to represent channel, we have a function which is called as C of tau comma t, right? This is how we represented channel, that is C of tau comma t. And if we are taking the Fourier transform, where I mean Fourier transform with respect to t, we are taking the Fourier transform with respect to t, and then that term is called as the scattering function, and scattering function is represented by sc of tau comma rho. Scattering function is represented by tau comma rho. Can you tell me what are the components that we can uh, observe from a scattering function? See, when we started this class, we told that it is all about two, three parameters, right? So when we talked about the channel, we mentioned that there is something called as a multipath effect, because there are multiple scatterers, and because of this multiple scatterers, we had this multiple components, right? That effect is called as the multipath effect. Similarly, because of the movement of the transmitter and receiver, we had something called as the Doppler effect, right? So wideband channel is, I mean, the effect that is that can be pulled to while considering scattering function is called as the multipath effect and Doppler effect. So we can mention the first component, that is tau, as the parameter that describes the multipath effect. Tau describes the multipath effect, right? And how can we tell that tau describes the multipath effect? Because if we are transmitting one component and after some time tau, it is received at the receiver, tau 0, tau 1, tau 2, etc. So that means tau describes the parameter, tau describes the multipath component, right? And and rho describes the Doppler effect, which is due to the movement of transmitter, relative motion of transmitter or receiver, right? So characterizing wideband channel is all about mentioning the multipath effect and the Doppler effect. Okay, so here we have the channel that is C of tau comma t, right? We have the channel C of tau comma t, and we are taking the Fourier transform with respect to t. So can you tell me what is the parameter that is being that we can observe in the scattering function sc of tau comma rho? And you have to tell me why we are going to observe that particular function. Are you getting the question? See, we have the channel that is C of tau comma t, right? We are describing the channel by C of tau comma t. So by taking the Fourier transform with respect to t, what are we trying to observe? What are we trying to analyze if you are taking the Fourier transform when we do the, when we do the Fourier transform with respect to t?
Sir,
See, these are the small things that describes the entire wireless communication and wideband channel, etc. If you uh, focus on these small parameters, then understanding this wireless communication is very easy. Yeah, tell me,
so,
what are we trying to observe? What
sir,
are we trying to
so,
capture?
excuse me, sir.
Yes.
Yeah, so basically, SC of tau comma rho is telling us that for any given frequency, how much delay it's experiencing because of scattering on the multipaths.
No, I'm not sure about answering that statement. I mean, whether that is right or wrong. But it is not about delay. That is the point. See, we are converting C of tau comma t, right? We are converting C of tau comma t, and the corresponding Fourier transform pair is SC of tau comma rho, which means that you are doing Fourier transform with respect to t. You are not doing the Fourier transform with respect to tau. You are not doing Fourier transform with respect to tau. That is you are not analyzing the tau component. You are not spreading the tau component. You are spreading something that is in the time domain, that is t domain, right? So let me ask you some basic questions. What is the Fourier transform of an impulse? Impulse is in time domain. What is the Fourier transform of an impulse? Okay, forget about Fourier transform, etc. If you have something like an impulse in time domain, what is the corresponding signal, or what is that something in frequency domain? Forget about DFT, DTFT, Fourier transform, etc. You have something in time domain that is called as impulse in time domain. What will you get in frequency domain?
A constant in frequency domain.
You will get a constant. You will get something that is present in all frequency, right? You have something like a line, right? It's something like this. It's frequency. This is positive. This is negative. So you have a constant, all right? So same thing is being, you're doing the same thing here. So you are trying to convert something in time domain to frequency domain. So if you observe that something in time domain, it is C of tau comma t. So you are keeping that tau constant here. You are not touching that tau here. C of tau comma t. And if you are comparing C of tau comma t and the corresponding frequency component SC of tau comma rho, tau is still there in SC of tau comma rho, right? Tau is still there. And what you are trying to elaborate, or what you are trying to analyze, is the T component. That means you are trying to analyze the Doppler effect. You are trying to analyze the Doppler effect here. So SC of tau comma rho captures the Doppler effect. Are you getting the idea behind SC of tau comma rho? So you have the channel C of tau comma t, and if you are taking the Fourier transform, if you are taking the Fourier transform with respect to t, the corresponding Fourier transform term is SC of tau comma rho. So if you are taking that Fourier transform with respect to t, you are trying to capture the Doppler effect. You are not trying to analyze the multipath effect. You are trying to capture the Doppler effect. Okay, so that's all about scattering function. So we have seen delay spread, and we can analyze whether the channel is narrow band or whether the channel is wide band from delay spread. And we have seen scattering function. So if you have something like SC of tau comma rho, then we know that it is meant to analyze the Doppler effect, right? Okay, now let us assume that there are two components between transmitter and receiver. Okay, we have the transmitter here. If you can look at this diagram, you have the transmitter here, TX is there, RX is there. So you have two components, path 1 and path 2. And these two components have the delay tau 1 and tau 2. So let us say that two components have the delay tau 1 and tau 2. And the autocorrelation function can be written as AC of tau 1 comma tau 2, then t comma t plus delta t, right? This means that we are trying to observe the values at the receiver at different timings, t1 and t2, or we can write t1 and t2 also as a also in another notation, that is t and t plus delta t, right? You can write it either as t1 comma t2, or you can write it as t comma t plus delta t, which means that you are observing two components at two different timings. Okay, now we assume that the channel is WSS. It means that it is wide sense stationary. What is WSS? WSS is WSS is wide sense stationary. And the important parameter to be noted is that it is stationary. That is, it is time invariant. It is not varying with respect to t. It varies with respect to, I mean, the parameter to be analyzed here is tau. So we are neglecting the t parameter and we are considering only tau and delta t. That is the delay between these components. So AC of tau 1 comma t2, I mean tau 1 comma tau 2, t comma t plus delta t can be written as AC of tau 1 comma tau 2, then delta t, by assuming WSS, that is by assuming wide sense stationary channel. And the equation for that is expectation of C star tau 1 t into C of tau 2 t plus delta t. So this is a standard expression for how you observe the autocorrelation. So this is the expression for autocorrelation. Okay. Now we have the autocorrelation function of C, that is the channel C of tau comma t, which is written as AC of tau 1 comma tau t, tau 2, then delta t. Okay. Now how should I put it? Okay. Okay, we'll see. We'll also consider another assumption that, see, we have just seen one equation of autocorrelation function, AC of tau 1 comma tau 2 comma delta t, and we are assuming one more thing, that is, instead of this tau 1 comma tau t, we'll be putting it as tau, which is equal to tau 1 and tau 2. So the equation AC of tau 1 comma tau 2 delta t can be written as AC of tau delta t. Okay, is it little bit confusing here? Like the whole, the mathematics and all. See, the thing is that the textbook Andrea Goldsmith is written in such a way that you have to understand, I mean, have to go through all this autocorrelation, scattering function, delta t, tau, etc., etc. Okay, so the idea is that you consider two different components at two different timings, and you have to analyze the correlation between two different components. Okay, let us say that there are two components at two different okay, I'll try to avoid the mathematics jargon here, and I'll try to put it simply in a pictorial way. Okay. So what we have seen earlier is that we have the autocorrelation, that is AC of tau comma delta t, and we are taking the Fourier transform, right? And this time what we are doing is that we are taking the Fourier transform by multiplying, I mean, with respect to delta t, with respect to delta t. So the autocorrelation function is here, and we are trying to take the Fourier transform with respect to delta t. And this time we have the scattering function as SC of tau comma rho. And similarly, I mean, as I have just mentioned earlier, the first component represents the delay and second component represents the Doppler. So first component represents the multipath and the second component represents the Doppler effect, which is the essential part of, which explains the multipath nature. I mean, which explains the wireless channel. Okay. Now coming to the division of wideband channel. Okay, we can divide the wireless wideband channel based on two parameters. Okay, based on two parameters. One is based on multipath, second is based on the Doppler effect. Okay, you can, for time being, you can forget whatever is considered earlier, that is the mathematics, autocorrelation, Fourier transform, etc. And you can listen to this division. So wideband channel can be divided based on two parameters. One is multipath, and second is Doppler. And do you know what are the different classification based on the multipath? We can classify the channel into two based on multipath, and similarly we can classify channel into two based on Doppler. Can someone tell me? And I think you might have seen this somewhere. Have you seen these terms frequency selective channel, and flat fading, fast fading, and slow fading? Have you seen these terms? So the first two terms, that is the frequency selective channel and flat fading, are there because of the multipath effect. So based on multipath effect, we can classify the channel as frequency selective or flat fading channel. Okay, first one is frequency selective and second one is flat fading. And based on the Doppler effect, we can classify the channel as fast fading channel and slow fading channel. So what I'll be doing today is that I'll be describing the the frequency selective and flat fading channel, which is due to the multipath, and I won't describe the fast fading and slow fading channel, which is due to the Doppler effect today. So in today's class, we'll be seeing the frequency selective channel and flat fading channel, and we'll leave the next topic, that is the effect of Doppler effect, to the next class. So I think we can wind next class in like 1 hour, and then I can leave class to HSM sir. Okay, so what I said is that the channel can be divided based on multipath. Similarly, channel can be divided based on Doppler. So there are some terms that are written here: power delay profile, coherence bandwidth, Doppler power spectrum, coherence time, etc. So the first two terms, power delay profile and coherence bandwidth, are related to multipath. Similarly, the last two terms, Doppler power spectrum and coherence time, are related to Doppler effect. Okay, so today we'll be considering the first two terms, why these are important, why power delay profile is important, and why coherence bandwidth is important, and we will see these parameters today. And in tomorrow's, Thursday's class, we'll see what is meant by Doppler power spectrum and coherence time. Okay. So we have seen this diagram earlier when I have mentioned about the channel response and all. So there are multiple observations at a particular time. You can see here that there are two axes. One is t here, and one is tau here. So t means we are observing at different time instance, right? We are observing at different time instance. Let us say that you're observing the channel at T1, right? Or you are observing the channel at T2 or T3, etc. So T is all about at what time you're observing the channel. And tau is about delay. And there is a transmitter, there is a receiver. You are transmitting something like you are transmitting a pulse from transmitter, and due to multipath, it is observed, it is received at the receiver at different time instance. So these delays are captured in tau. These delays are captured in tau, which is due to multipath. So coming to power delay profile, we have seen this particular function earlier, that is AC of tau comma delta t. And coming to power delay profile and multipath effect, we put delta t is equal to 0, and we analyze the function from a particular time instant only. We analyze the function from a particular time instant only. That is, we are not looking at different time instance, that is t1, t2, t3, t4, etc. We see this function from a particular time instant, that is, let us say t0. We are fixing on to t0, and then we are analyzing the power that is received at the receiver. For example, if you stick on to T0, you can see that there are multiple components that are received at a receiver. So this is one is here, second component, third component, fourth component, etc. Okay, you have to look from the left side, that is, you are sticking on to T0. You are not considering T1, T2, T3, etc. You are taking only T0, and then fixing T0, you are observing multiple delay values, right? So at T0, you are having multiple components, which is like this: tau 0, tau 1, tau 2, tau 3, etc. Right? So these diagrams captures effect of multipath. Right, these diagrams captures the effect of multipath. Okay, so it means that by setting delta t to 0, the autocorrelation, we are trying to analyze the autocorrelation relative to delay at a fixed time. Okay, we are not trying to analyze different time instance, that is T0, T1, T2, T3, T4, etc. We are trying to analyze the autocorrelation at a particular time, that is T0 or T1, T2, T3, etc. So we are sticking on to a particular time and then we are trying to analyze the autocorrelation. And what are the parameters that we can analyze when we have such a diagram? When we have a diagram which is something like this, the parameters are average delay. You can see it here. Average delay, RMS delay spread, and then there are something called as maximum delay, etc., etc. And but most of the textbooks stick on to these values. I mean, the important parameters that we can get from these kind of diagrams are average delay, that is mu tm, and RMS delay spread, that is sigma tm. Okay, so what is power delay profile? Power delay profile is something like this, where we observe different power values, where the variation is with respect to tau. Variation is with respect to tau, that is the delay. And we are fixing onto the time. We are observing at a fixed time. We are observing the autocorrelation at a fixed time. Okay. So that is all about power delay profile, and now we'll see how this values can be calculated. So as I have just mentioned, there are two important terms that we can absorb from this particular diagram, that is power delay profile, and two important values are average delay spread and the second value is RMS delay spread. So average delay spread can be calculated, that is mu Tm is equal to integral 0 to infinity tau into autocorrelation d tau by integral 0 to infinity AC tau d tau. So this is how we calculate average delay spread, right? This is how we calculate average delay spread. And once we have this value, what we are going to do is we will put this value here, mu Tm, and then we'll find RMS delay spread. So sigma Tm is equal to root integral 0 to infinity tau minus average delay spread whole square into AC tau d tau by integral 0 to infinity AC tau d tau. So the denominator is same. Only thing is that you are adding some, you are adding the value that you have found in the first equation to find second equation. Okay, so you can find two values, that is average delay spread and RMS delay spread, once you have power delay profile. So what are these value actually? Which parameter you are trying to analyze by using average and RMS delay spread? Is it Doppler or is it multipath? So the answer to that is we are trying to capture the effect of multipath using average and RMS delay spread. We are not trying to analyze the Doppler effect here. We are trying to analyze the multipath effect by using these parameters, that is average delay spread and RMS delay spread. Okay, so what are the ill effects here? Why are we looking at distortion, etc.? Why are we looking at average delay spread? So the idea is that let us consider a direct path. Let us consider a transmitter is transmitting signals in series like S0, S1, S2, S3, S4, S5, etc. So there is a transmitter that is transmitting signals S0, S1, S2, S3, S4, S5, etc. So assume that there is something called as a direct path between transmitter and receiver. So the first the first components is received in a diagram something like this. That is, it starts at this particular time. Okay, and then the NLOS scattering path begins after ROT, that is delay spread. This is nothing but delay spread. Okay, so in the NLOS path, the component starts, the S0 component starts after the time ROT. Okay, so there is a direct path and there is an NLOS path. So the direct path starts here. S0, S1, S2, S3, S4, S5 are transmitted. Then in the NLOS path, the S0 component is transmitted after a time rho t. Sorry, sigma t, which is the delay spread. Okay, so what is the problem here? See, let us, if you see this diagram, what is the ill effect that is caused due to the delay in transmitting S0 here? Any idea? See, the question is, you have two paths. One is the direct path, another is the NLOS path. And in direct path, signals are transmitted in order, that is S0, S1, S2, S3, S4, S5, etc. But in NLOS path, signal is transmitted after some particular time, and that time is called as delay spread. Okay. So after sigma tau, S0 is transmitted. And what is the effect due to that delaying of transmission?
Excuse me, sir.
Yeah.
So
What will
at
happen?
at the receiver, we are going to get a combination of both these signals at the same time.
Yes.
So
Yes.
when the direct path tells us that we'll be receiving a low S1 signal, the delayed analogous path is telling we are getting a high S0. So there's interference and you can't extract the data.
Yeah, partly right, partly wrong. And the thing, it is not low S1, low high S0. We are just transmitting S0, S1, S2, S3. S1 can be high also, right? S1 can be high, S3 can be high, S5 can be high. It does not mean that S1 is low. And the idea is to represent that we are transmitting a whole different signal during that particular time, during that S1 time. So the problem here is that at receiver, if receiver is trying to retrieve S1, by the time receiver is trying to retrieve S1, the NLOS path will be, the signal that is being received from the NLOS path is S0. It is not S1. So there is some kind of distortion. The receiver will be happy if it is S1. If it is both S1. But unfortunately, it is not both S1. It is S1 and S0. And since there is a mismatch, here, one is S1 and one is S0. And since there is a mismatch here, there is something called as a distortion here. And that distortion is technically called as inter-simple interference. Okay, that means that if this delay is more, if the delay is more in that NLOS component, there is something called as, there is some ill effect, and that ill effect is the distortion, and that distortion is called as inter-simple interference. So if you can look at this equation, if sigma tau, if the delay is greater, How much greater? If the delay is greater than Ts, if sigma tau is greater than Ts, then there will be a distortion, and that particular distortion is called as inter-symbol interference. Okay, so that is all about the first case. But if you look at the second case, you can see that sigma tau is less, right? If you can see the second, if you can see the second figure, sigma tau is very less compared to Ts. So that uh, at this time, receiver can have both S0 here. In first case, it is S0, and in second case, it is S0. So it can easily recover the first symbol, that is S0, right? So if sigma tau is less, then there is no distortion. There is no distortion in the receiver. That is, there is no inter-symbol interference in the receiver, right? So that means sigma if sigma tau is less than Ts, that is symbol time, sigma tau is less than Ts, then there is no ISI, no ISI. But if sigma tau is greater than Ts, then there is inter-symbol interference. Is it clear? Is it clear?
Yes, sir.
Yeah. So this is how we classify the channel based on the multipath effect, that is based on the delay spread. Okay, now we'll see some problems. Okay, so consider a wideband channel which is represented by AC of tau, which is equal to e raised to minus tau by 0.00001, which is during the delay, that is 0 to 20 microseconds, and 0 during all the other time. So what you have to find the average delay spread and RMS delay spread. Okay, can you try? Just see that are you getting the same answer. See, if you are trying to read this particular portion, you can either opt for Andrea Goldsmith, and if you are not understanding it, if you feel that the language is very difficult, you can go to Rappaport or textbook by Aditya Jagannathan sir. But I request you to have a look at Andrea Goldsmith textbook first, because these terms, autocorrelation, scattering function, etc., uh, are considered in that textbook more often compared to you know Rappaport. So it will be better to go to Andrea Goldsmith, the textbook by Andrea Goldsmith first, and then if you are not understanding, you can refer to the other two textbooks for clarifications. Okay, have you got the same answer?
Yes, sir.
Everyone? Okay, so why are we doing this? Why are we calculating this entire, average delay spread, RMS delay spread, etc.? Is there any advantage? So answer to that is, see, we have the average delay spread as 6.87 microsecond here, and we have RMS delay spread sigma Tm as 5.25 microsecond. And we have seen that in order to avoid in order to avoid ISI, we have to choose TS. We have to choose TS, which is greater than sigma Tm, right? So what is this condition? If TS is greater, if TS is greater than sigma tau, then there will not be any ISI, right? If Ts, that is the symbol time, is greater compared to the delay spread, then we will not be having ISI. So this is the condition for no ISI. That is, we need to have Ts which is much greater than symbol time which is greater than delay spread. So we need to have a very high symbol time considering the delay spread. And we have the channel characteristic in RMS delay spread. That is, we have the RMS delay spread as 5.25 microsecond. So our aim is to avoid inter-symbol interference. And how can we avoid inter-symbol interference? We have to choose a symbol time such a way that it is higher than the delay spread. So one rule is that we have to choose some TS which is greater than 10 times the delay spread value. We have to choose TS. We have to choose TS which is greater than 10 times the delay spread value. That is, TS is greater than 10 into sigma Tm. So we have sigma Tm as 5.25 microseconds. So what you have to do is we have to take, can you multiply this, that is 10 into 5.25 microseconds, and then if you multiply 5.25 microseconds into 10, you will get TS, right? You will get TS, and the rate at which the transmitter can transmit or the communication system can be designed is Rs equal to 1 by Ts. R is equal to 1 by Ts. So what is Rs? Rs is the rate. Rs is the rate. The transmission rate. Yeah, can you please do this calculation? What will you get if you have 1 by, if you do this 1 by 10 into 5.25 microseconds?
Sir, we get 19.036.
It's same, right? Yeah, okay.
Yes.
So Rs is equal to 19.04 kilo symbols per second. So what is the main idea behind this calculation? The idea is that if you are transmitting at this symbol rate, that is 19.04 kilo symbols per second, if you are transmitting at this particular symbol rate, then there will not be any ISI. Right? If you're transmitting at 19.04 kilo symbols per second, then TS will be sufficiently large. TS will be sufficiently large, and it is much greater than the, what you call it, RMS delay spread. TS is greater than RMS delay spread, and under that condition there will not be any ISI, there will not be any inter symbol interference. Okay, now can you tell me what will happen if the transmission rate is 1 megasymbol per second? What will happen if the transmission rate RS is equal to 1 megasymbol per second?
There will be ISI, sir.
Yeah, then what is TS now if you're transmitting at 1 megasymbol per second?
T is 1 microsecond.
Yeah, that is 1 mega means 10 raised to what, 6, right? So 10 raised to minus 6 is 1 micro. So TS will be, if you're transmitting at 1 mega symbol, TS will be 1 microsecond. That is TS. And sigma TM is, what is sigma TM? 5.25 microseconds. So TS is small here. TS is small here. So since TS is small here, we'll see inter-symbol interference in the receiver. Is it clear? So based on the characteristic, based on delay spread, we have to decide. We have to choose the transmission rate. We have to choose the symbol timing. It is not a random thing. We cannot simply decide that, okay, let the communication system transmit at 1 mega symbol, or let the system transmit at 1 kbps, or etc, etc. So we have to take some parameters, and then after considering these parameters, then we have to decide what should be the transmission rate. Okay, now does it make sense then, like why we are using this average delay spread, RMS delay spread, etc. Okay, now see, we have seen the equation that is being used in Andrea Goldsmith textbook, that is to find average delay spread. In order to find average delay spread, what we did is we integrated, that is 0 to infinity tau AC tau d tau by 0 to infinity AC tau d tau. So this is how we found average delay spread. But in Rappaport, in the textbook by Rappaport, we can see that he has mentioned a different kind of equation. That is, instead of integration, he has mentioned it as summation. It has summation. That is, instead of integration from 0 to infinity, what it is, he used the summation term. That is integral, summation I equal to 0 to L minus 1 tau I gi by summation I is equal to 0 to L minus 1 gi. So both these equation, that is equation 3 or equation 4, if you number like this, equation 3 and 4 means the same, right? Integration and summation essentially means the same. If number of summation is higher, if you add infinite number of components, then it is almost like a integration term. So instead of integration, we can represent the same thing using summation term. So delay spread can be written, can be found using another set of equation, that is summation I is equal to 0 to L minus 1 tau I gi by summation I is equal to 0 L minus 1 gi. Okay, now we will find this average delay spread using this new set of equations. So instead of equations that we have used in Andrea Goldsmith, which is kept to the right, so these equations these equations, that is equations in the right side, these are used in the Andrea Goldsmith's textbook, but the two equations to the left are used in Rappaport's textbook. So you can find average delay spread and RMS delay spread using these two techniques. The difference is that in Andrea Goldsmith's textbook, she used integration, I mean the equation based on integration. But in Rappaport's textbook, what he did is he used equations based on summation. Though it means the same, you have to, what you have to do is you have to see the data. If it is based on integration, you have to go for equations in the right side. And if it is based on these kind of tables that you can see, you have to go for summation kind of equation. Okay, now there is a table here. There's a table which has some tau values and some gain, that is G values. So for 0 microsecond, the gain is minus 20 dB. For 1 microsecond, the gain is minus 10 dB. And for 3 microsecond, the gain is 0 dB. For 5 microsecond, the gain is minus 10 dB. What you have to do is you have to find the average delay spread and RMS delay spread. You have to find average delay spread and RMS delay spread. So before doing that, can we represent this using a power delay profile? Can we represent this using a power delay profile? We'll just try how we can draw a power delay profile. So just draw a line, time instance, that is, this is tau. So it's 0, 1, 2, 3, 4, 5. Okay, now we are considering how can I, yeah, yes, let us consider axis here. The first one is at minus 20 dB, which is the maximum one, which is contributing maximum. This is the 0 dB. So I'll draw 0 dB here. This is 0 dB, 0 dB. And which is next? This is 0 dB, and which is next? Minus 10 dB at 1 microsecond and minus 10 dB at 5 microsecond. So what I'll do is I'll mark it here minus 10 dB, and similarly at 5 I have minus 10 dB. Yeah, so this is minus 10 dB. Similarly, this is minus 10 dB, and again minus 20 dB, which is at 0 microsecond. So I'll mark it here minus 20 dB. Okay, so these are the components. So you have 4 components, that is L is equal to 4. There are 4 components. One is minus 20 dB, another is minus 10 dB, then 0 dB and minus 10 dB. So this is how you draw a power delay profile. And you have to note one thing, what I have drawn here is not in a proper scale, but when you draw, you have to consider some proper scale and must be neat. Since this is a EPAD, I cannot, it is practically impossible to draw good lines and all. Okay, now what you can do is you can find average delay spread and RMS delay spread. So what is the equation for average delay spread and RMS delay spread? First one we will find average delay spread. right? We'll find average delay spread. So it can be represented using mu Tm. Average delay spread is equal to tau I into Gi, right? Tau I into Gi. Remember, before doing any calculation, you have to convert the dB scale value to linear scale value. You have to convert dB scale value to linear scale value. So this is the main, the main mistake that people do. They'll simply put -20 and -10, which is wrong. You have to convert it to linear scale, that is 0.01, 0.1, etc. And then you have to do the calculation. So average delay spread, tau I Gi. So what is the first component? What is tau 0 and G 0? What is G0? G0 is nothing but 0.01. What is tau 0? Into 0 plus, then again, look at this table. It is easy, right? Then what you have to do is you have to write 0.1, that is tau 1 into G1, that is 0.1 into 1, 0.1 into 1 plus the third component, that is 1 into 1 into 3 plus 0.1, 0.1 into 5. So these are the set of tau I Gi's, right? Tau I summation tau I Gi. Now summation Gi, that is 0.01 plus 0.1 plus 1 plus 0.1. So can someone tell what this is? Put this in a calculator and tell the answer.
Sir,
Sir,
is it 2.97 microseconds?
Yes, it is 2.97 microsecond. Remember, I haven't added any microsecond term here. So the answer is in microsecond. So the answer is 2.97 microsecond. And now we have the average delay spread. And we have to find one more term, that is RMS delay spread. So what is RMS delay spread? RMS delay spread is equal to sigma Tm, which is equal to, how can we do that? We need to have G0 first, right? The first gain. G's correspond to the gain, that is G0 in linear scale. So first component is 0.01, and then we are going to multiply it to, yeah, I'll change. Okay. So equation is tau I minus average delay spread. Tau I minus, so this tau bar is nothing but average delay spread. So tau I, that is 0 minus 2.97 square, right? Plus the next term. Next term is 0.1 into what is the value here? Tau 1, what is tau 1?
minus 2.97.
1 minus 2.97 whole square, right? Plus 1 into what is the next component? 3 minus 2.97 whole square plus 5, not 5, sorry, 0.1, right? Yeah. Yeah, so Gi, the last, that is G3 is 0.1, 0.1 into 0.1 into 5 minus 2.97 whole square, right, divided by same thing, that is sigma GIs, that is 0.01 plus 0.1 plus 1 plus 0.1. And did I miss anything? Is it right?
Yes, sir.
No, it is not right. We have missed a square root term. See, there is a square root term here. It is root of summation gi to I minus average delay spread by summation gi. So there is a square root term here. Now you tell me the answer.
Sir, I'm getting 0.857 microsecond.
Yeah, it is 0.857 microsecond. Yes, so we have the average delay spread as 2.97 microsecond and RMS delay spread as 0.857 microsecond. Okay, now there is one more thing to remember, that is here you have 4 tap channels. There are 4 multipath components, right? One is at minus 20 dB, second is at minus 10 dB, and then third one 0 dB, then minus 10 dB. So practically, if you take a power delay profile, it is possible to have n number of components, right? Multiple number of components, and some may be invalid also. So some components which are very minute, like something like this, will not be considered when you calculate the power delay profile. Okay, some minute components can be neglected when you calculate these values, calculate the delay spread values. Okay. Now we'll come to another term, that is coherent bandwidth. So till now, what we did is we have mentioned that we are modeling, we are explaining multipath, the behavior of multipath, and then we have mentioned few technical terms, that is delay spread, average delay spread, RMS delay spread, etc. So the frequency domain version of delay spread is called as coherence bandwidth. The frequency domain, see, where is this point? Yeah. See, we have delay spread here. We have explained what is delay spread and the ill effects caused by delay spread, and we have explained the diagram in time domain, right? So if you consider the effect in frequency domain, the frequency domain version of delay spread is called as coherence bandwidth. So basically, two terms, that is delay spread and coherence bandwidth, are associated with coherence bandwidth and delay spread are associated with multipath components. So these two terms are associated with multipath. Okay, so you have delay spread in time domain. Similarly, you have coherence bandwidth in frequency domain. Okay, and now based on these two components, based on these two parameters, what we'll do is that we can divide the channel into two different channels. That is, one is frequency selective, and second is frequency flat or flat fading channel. So based on these two values, we can say that the channel is frequency selective or frequency flat channel. So we can say this in terms of delay spread. Similarly, we can say this in terms of coherence bandwidth. Okay. Now we have, yeah, so this is the rough relationship. If you see this equation, that is BC, that is coherence bandwidth, coherence bandwidth is roughly equal to 1 by delay spread, is roughly equal to 1 by delay spread. See, we'll see different versions, that is coherence bandwidth is equal to 0.02 by delay spread, it is equal to 0.2 by delay spread, etc. But roughly we can say that these two terms, that is coherence bandwidth and delay spread, are inversely, I mean, are BC is equal to 1 by delay spread, right? So this is the rough relationship, and we'll see why it is 0.02 by delay spread and 0.2 by delay spread, etc. So you can see this equation, BC is equal to 0.02 by delay spread, or BC is equal to 0.2 by delay spread. So there are multiple equations that are used in different papers. If you see different research papers, people come up with different kind of expressions. So coherence bandwidth can be, roughly we can say that coherence bandwidth is proportional to 1 by delay spread. So that is a rough comparison. It is inversely proportional. Now we'll plot some diagrams. That is, you can see the diagram to the left. That is, we are plotting AC of tau with respect to tau. We are plotting AC of tau with respect to tau, and this is the autocorrelation of C of tau comma t. This is the autocorrelation of C of tau comma t. Okay, and from this diagram, what we can observe is we can get values like average delay spread. What else? What are the parameters? Yeah, RMS delay spread, maximum delay spread, etc. So once we have this diagram, that is AC of tau with respect to tau, we can calculate values like delay spread, that is average delay spread, and RMS delay spread, then maximum delay, etc. So this is AC of tau with respect to tau is nothing but it is the autocorrelation value of C of tau comma t. And to the right, what you can see is the autocorrelation of C of f comma t. See, there is a difference. In the left, you have C of tau comma t. To the right, you have C of f comma t. Okay, so if you plot, the autocorrelation of C of f comma t, you have the dark line as the channel. You can say that this is the channel here, and there are two signals here, which is the narrowband signal and wideband signal, and this signal corresponds to the frequency selective signal, and the signal inside is called as flat fading signal, right? And we'll see why it is flat fading and why it is frequency selective fading. So basically what I'm trying to say is that there is a relation between delay spread and coherence bandwidth. Okay, you can see here there is a relation between delay spread and coherence bandwidth. Okay, so one is represented in time domain and second term is represented in frequency domain, and coherence bandwidth and what you call delay spread are inversely proportional. Okay, now we will see some diagrams of delay spread and coherence bandwidth. So the first diagram is in time domain. Right? Delay spread is something that we calculate in time domain, and coherence bandwidth is something that we calculate in frequency domain. So let us consider case A, that is you have sigma tau, which is equal to, I mean, at 0 microsecond, you have something like a spike at 0 microsecond. So the corresponding frequency domain version is the constant signal. Okay, so if you have a spike for a delta function in the time domain, the corresponding signal is something like this. Similarly, if you look at case E and F, if you have some spike in frequency domain, then the same thing, I mean, the similar thing will apply in the time domain. That is, you will see a constant signal in the time domain. But if you see case C and D, you can see that there are two parameters. So this is delay spread, and if you plot the corresponding, the frequency diagram, signal in the frequency axis, then you will see the parameter BC, that is coherence bandwidth. So the idea behind explaining all this thing is that by using these parameters, delay spread and coherence bandwidth, you can model multipath. Or rather, we can say that if you have the value delay spread, you can understand what is the value of coherence bandwidth. Or similarly, if you know what is coherence bandwidth, then you can identify what is delay spread, because it is inversely proportional. Okay, now we'll come to the important findings, to the conclusion, that is what is flat fading and what is frequency selective fading. Okay, so if the coherence bandwidth is high, then we call such a system as flat fading system. If the coherence bandwidth is high, then we call such a system as flat fading system. That is, if coherence bandwidth is greater than signal bandwidth, then we call such a system as flat fading system. Okay, so why are we calling it as flat fading system? The answer to that, you can see this diagram. You have this one, this is the input signal, and you have the channel here, right? You have the input here, you have the channel here. So if you multiply x of f, the input is represented by x of f, channel is represented by h of f. So if you multiply x of f and h of f, you will get y of f, right? You'll get y of f. So if you compare x of f and y of f, there is not much distortion if you compare the input signal spectrum and the output spectrum. See, if you compare x of f and y of f, there is not much distortion. It is undistorted, right? So such a system is called as flat fading channel. But on the other hand, if you have the signal bandwidth much higher, if you have the bandwidth of the signal much higher compared to the channel, compared to the coherence bandwidth, then there is significant distortion. So you can look at this diagram to the right. You have x of f here, and you have h of f here, and sorry, h of f here, and if you multiply, you will get y of f. So just have a look. That is, if you compare x of f and y of f, it is not same. X of f and y of f are not same. It means that there is significant distortion in the transmitted signal. There is significant distortion in the transmitted signal. So that means if BS is greater than BC, there is distortion. If BS is greater than BC, there is distortion. But if BS, that is signal bandwidth, is less than coherence bandwidth, if signal bandwidth is less than coherence bandwidth, then there is no distortion. Okay, so there are two situations. One is flat fading, where signal bandwidth is less compared to coherence bandwidth, and second is frequency selective fading, where signal bandwidth is higher compared to the channel bandwidth, that is coherence bandwidth, which means that in frequency selective fading you can see considerable distortion compared to the previous one. Okay, so we have mentioned this in terms of coherence bandwidth, that is, if symbol bandwidth is greater, if less compared to coherence bandwidth, then we have flat fading. Similarly, if we have signal bandwidth which is greater than coherence bandwidth, then we have frequency selective bandwidth. And I have already mentioned that we can also say this in terms of time domain, in time domain, that is using delay spread. That is, if Ts is greater than sigma t, that is symbol time, if symbol time is greater than sigma t, that is delay spread, then we have flat fading. That means there is less distortion, right? We have already seen that. If you remember this diagram, see here Ts is less. Sorry, if you see a second case, see Ts is high. Compared to sigma tau. That is, there is no ISI. So we are going to see this. That is, if Ts is high compared to sigma tau, then we have flat fading. That is, there is no distortion. But if Ts is less compared to sigma tau, then there is distortion. You can see that there is distortion. That means that the channel is frequency selective. So for frequency flat fading channel, there is no distortion, but there is distortion in frequency selective channel. Okay, is it clear? What is flat fading and how can we represent it using two terms, that is delay spread and coherence bandwidth? Similarly, we can describe frequency selective fading in terms of delay spread and coherence bandwidth. Is it clear?
Yes.
So in flat fading, there is no distortion. You can simply compare, the figure in left and right. You transmit something, if it is received as it is, then there is no distortion, right? So you can compare the x of f and y of f in the left side, and then you can easily understand that there is no distortion. So in flat fading channel, there is no distortion, but in frequency selective fading channel, that is to the right, there is considerable amount of distortion. And why is it so? It is because of lesser coherence bandwidth and higher delay spread. Because of lesser coherence bandwidth and higher delay spread, we have some kind of distortion. and the name of that distortion is ISI, that is inter-symbol interference. Is it clear? So as I said, wideband channel can be classified based on two parameters. One is multipath, second is Doppler, right? So first one is multipath, and based on multipath, you can classify into two channels. You can classify into two channels. So based on multipath, you will get flat fading and frequency selective fading, which is represented in diagrams in left and right. Okay, now we'll see the impact on designing wireless communication system, impact of average delay spread and coherence bandwidth on designing of a wireless communication system. So let us consider the average delay spread sigma tau as 1.37 microsecond. So what is the coherence bandwidth here? What is the coherence bandwidth? Coherence bandwidth is nothing but 0.2 by sigma tau, that is 1 by 5 into sigma tau, which is equal to 1 by 5 into 1.37 microseconds, which is 146 kilohertz. So a system with average delay spread 1.37 microseconds, that is delay spread is 1.37 microsecond. Similarly, the corresponding coherence bandwidth is 146 kilohertz. So you have the term, technical terms corresponding to the multipath, that is delay spread and coherence bandwidth. Now, uh, consider two systems, that is AMPS, which is nothing but 1G system. This is the name for 1G system, and GSM is the name for 2G system. So AMPS has the bandwidth 30 kilohertz, signal bandwidth 30 kilohertz, and 2G system, that is GSM, has the bandwidth 200 kilohertz. Identify which is having which will experience flat fading and which will experience frequency selective fading. So what we have here is we have coherence bandwidth, that is 146 kilohertz. So we have 146 kilohertz coherence bandwidth, and we have 30 kilohertz, which is the signal bandwidth, BS or B, whatever. And since BS or signal bandwidth is less, we have such a system, and we call such a system as, what is the name for such a system? If coherence bandwidth is high, what is the name allotted to such a system?
Sir, it's
Can you tell me?
fading.
It is flat fading. So if coherence bandwidth is high, it is called as flat fading. And if in GSM 200 kilohertz is, anyway, you can see that it is higher, right? So signal bandwidth is higher compared to the coherence bandwidth. So such a system, we can call it as frequency selective fading. Frequency selective fading. So since GSM experiences a frequency selective fading, we need to add an equalizer in the receiver. We need to add equalizer in the receiver, because different frequency components experiences different effects. So in order to equalize that effect, you need to add something called as an equalizer. See, if you see this diagram of frequency selective fading, you are transmitting x of f, and if you see y of f, it is not same. It is not x of f, right? Some change has happened. So you need to equalize it. You have seen equalizer in music players and all. you tweak something, right? You adjust something, right? So same thing you have to, I mean, similar thing you have to do in case of frequency selective channel. That is, you have to add something called as an equalizer in GSM. But for IMPS, you need not add anything. You can, there is no distortion, and therefore you need not add any equalizer in AMPS. Is it clear? So what is the use of equalizer here?
So it is to recover the original input frequencies.
Yes, so since we have something called as a frequency selective fading or inter-symbol interference, to tackle that, to overcome that inter-symbol interference, we have to use something called as equalizer. Okay. Now I think we can stop, and in next class we can compare the division of channel with respect to Doppler. So you will see what is fast fading, what is slow fading, etc. So it's basically some 7 or 8 slides, and then I think I can stop. Then maybe we can, I'll be present, and then we can have a doubt clearance session or something like that. Okay, and any doubt in today's class?
Sir?
Yeah, just a second. Yes, yeah, tell me.
Yeah. So when we are talking about frequency correlation should be above zero point 0.5 or above zero point 0.9, what exactly do we mean?
Yes, I didn't explain that because see, there are kind of two different kinds of situation. That is, the channel correlation can be 0.9 or channel correlation can be 0.5. So there are uh, multiple situations that arise depending on the correlation. Okay, so depending on correlation, we can have different kind of equation for calculation of coherence bandwidth. Yeah, and to explain that, I may have to spend some 30 minutes or something. That's why I didn't spend much time. See, the idea is that what you can do is in this question, I mean, in questions, they'll be mentioning what is the correlation. And they'll be mentioning the correlation will be above 0.5 or correlation will be above 0.9. So based on that, we can use equations that is BC is equal to 0.2 by delay spread, or BC is equal to 0.02 by delay spread. Generally, as a rule of thumb, the equation that we use is second equation, that is coherence bandwidth is equal to 0.2 by delay spread. It depends on the correlation of two different frequency components.
So just for rudimentary understanding, it's okay to think of it as the degree of inter-symbol interference that's happening in the channel. Sort of.
See, if you need, I'll explain it a little bit. So you see, we have seen that it is, I mean, we have seen coherence bandwidth and delay spread, etc. Right? So what coherence bandwidth says is that you take two components, right? You take two components, and if it is outside coherence bandwidth, it looks like an independent component. It receives a different kind of treatment. Right? If you have F1 here, and if you have F2 here, and if it is more than, if F2 minus F1 is more than the coherence bandwidth, then two components, that is the component at F1 and F2, will be experiencing different kind of treatment. That is, it is not, this particular association is called as, I mean, this attachment is called as the correlation. So depending on the correlation of the component in F1 and F2, depending on the correlation in F1 and F2, we can decide what is the coherence bandwidth. Okay, so it is a little bit mathematical, and more than mathematical, it has a little bit concept and all. That's why I didn't focus on that.
Got it, sir. Thank you.
Yeah, so in a nutshell, what we have covered today is the classification of channel depending on multipath, right? So depending on multipath, we can classify the channel into two, that is frequency flat and frequency selective. And we used two parameters, that is coherence bandwidth and delay spread, which are inversely proportional. Okay, so this is the basic idea behind today's class. And similarly, we use a similar set of parameters for next day's class. That is, we use Doppler effect, and based on Doppler effect, we classify the channel as fast fading channel and slow fading channel. And there are two sets of parameters that we will use: coherence time, etc. So yeah, we'll see in next class. So today what we covered is multipath analysis of multipath channel. I mean, in next class we'll be covering analysis of uh, Doppler effect. Okay, that's it. Anything else? So my humble advice is that if you can read textbook by Andre Goldsmith, better. That is, I would suggest that you can go for that. And if you cannot, if you don't understand anything, because see, as a beginner, if you're trying to explore the terms in terms and concepts in wireless communication, it may be a little bit difficult to understand these terminologies, because each line will have a bigger concept. You can think of different concepts, diagrams, different papers in a single line. So it is in order to understand textbook, I mean this particular textbook, you need to have some basic idea of what wireless communication is. So in that case, if you don't understand Andrea Goldsmith, you can go for Rappaport, which I feel it is. I mean, the language in Rappaport is comparatively, easy, and it is also used in many good institutes like NITs and all. So use what you call a layman's language. If you want to understand from a very simple language, then you can go for textbook by Aditya Jagannathan. But in that case, you may miss some, some important points. So I I request you to follow the same, the flow chart. First, you go for Andrea Goldsmith textbook, then Rappaport, and if you still don't understand, you can go to Aditya Jagannathan sir's text. And you can also get the same, classes, the same topics by Aditya Jagannathan in YouTube's also, YouTube videos. Yes, so I think we can stop at this point. Or anything else? Any doubt? Yeah, then we'll stop. Thank you. And before we stop, what I would like to say is, for next class, since it is I need to cover only a small topic, that is explanation of channel classification based on Doppler. It is a small topic. Maybe I can cover it within some 40-45 minutes. So yeah, rest of the time I'll not take class, but I'll be online. If you can study topics and if you can ask doubt, then I'll be glad to answer. So I think we can stop. Thank you then.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.